Hello everyone, this is Professor He. Nice to see you again. The topic of this task is about the isobaric and isothermal process. Let's firstly talk about the isobaric process. Firstly, the definition of the isobaric process. Isobaric process is a process during which the pressure P remains constant. For example, a heat addition or heat rejection process can carry out while keeping the pressure constant. For example, the process performing in combustion chambers and boilers are commonly approximate isobaric process. Secondly, the process equation. For ideal gas, the process equation is. This means that during the isobaric process, the specific volume is proportional to the temperature. Thirdly, the PV and TS diagrams. These are the isobaric process shown in the PV and TS diagrams. Pay attention to the slope of the isobaric path line in the TS diagram and try to derive it. Actually, it can be found from the second DS equation directly. Recall the second DS equation, equation 532, that has been derived. The entropy change can be expressed as for the isobaric process. Fourthly, the calculations of work and heat. Without friction, the expansion work, the technical work, and the heat addition for the 1 kilogram working fluid for an isobaric process can be calculated as, where the properties such as enthalpies and specific volumes can also be obtained from property tables. The heat addition can also be determined by the first law directly. Now, let's talk about the isothermal process. Firstly, the definition of the isothermal process. Isothermal process is a process during which the temperature T remains constant. An expansion, a compression, a heat addition, or a heat rejection process exceeds while the temperature remains unchanged. For example, the isothermal process is performed in the condenser and evaporator. Secondly, the process equation. For ideal gas, the process equation is. This means that during the isothermal process for an ideal gas, pressure and specific volume maintain an inverse relationship, or the products of pressure and specific volume maintain constant during this process. We can easily find the property relations during isothermal process for an ideal gas. Based on the first and second DS equations, equations 530 and 532, we have expressions of entropy change for an isothermal process. Also, we have expressions for changes of internal energy and enthalpy, which are 0 for ideal gas proceeding an isothermal process. The relations during isothermal process are summarized as: thirdly, the PV and TS diagram. These are the isothermal processes shown on the PV and TS diagrams, where path 1 to 2 is the expansion process, and path 1 to 2 apostrophe is the compression process. Pay attention to the slope of the isothermal path line in the PV diagram and try to derive it. Actually, it can be found directly from the first and second DS equations. Fourthly, we come to the calculations of work and heat. Without friction, the expansion work and technical work by the 1 kilogram of ideal gas proceeding an isothermal process can be calculated as follows. From the process equation below, we then conclude that the expansion work is identical to the technical work by the 1 kilogram of ideal gas. These are some summaries for the isothermal process. Without friction, the heat exchange during an isothermal process is, according to equations 443 and 446, the entropy change in an isothermal process for ideal gas is. Applying the first law of thermodynamics to the isothermal process, we have. Therefore, for an isothermal process of ideal gas, we have. This means the amount of the compression work, the technical work, or the heat exchange is identical for an isothermal process. Okay, that's all for this task. Thank you very much, and see you next time.